Hello, this is my second video, and here I'll be talking about the Bernoulli integral. This is an integral I came across while studying the gamma function, which in the solutions I've seen for this problem, this integral, the gamma function seems to always be a part of it. Instead of just solving the integral as is though, I thought I'd solve a more general case. The limits stay the same, but x is also raised, x is raised to the ax and raised to the b for a and b strictly greater than or equal to 0. This will make more sense as seeing the final solution, as the final answer I'll come up with will be in series form, and for some values of a and b, when you allow these values to be less than 0, the integral or the series become undefined, and so they aren't equal to each other. Thus, by keeping a and b greater than 0 or equal to 0, the integral and the series will always be equal to each other. To continue from here, we'll just do the general case, general proof, or solution, where we'll raise to the e, and we'll get a x to the power of b times the natural log of x dx. That's terrible. Here, raising to the power of e and having the natural log of x, they undo each other by logarithm rules. And then from here, we can just use the series expansion of e to get the infinite series of a times x to the b times the natural log of x all to the n divided by n factorial. Now we're going to pull the series, the infinite series, out of the integral. You can do this for every finite series, but you can't do this for all infinite series. You can't necessarily assume an interchange of limits. In this case, you can, but the explanation is probably beyond the scope of this video, so maybe I'll save that explanation for a different video. But for here, just know, it is allowed. That should be a 0, not a 1. Now in doing this, n here is going to just be a constant, so we can pull that out as well, n factorial. And we get the integral from 0 to 1 of a to the n times x to the nb times the natural log of x to the power of n with respect to x. Here you might notice a to the n is also just a constant, so we'll pull that out as well. Now from here we need to do a substitution. So I'm going to let negative r equal the natural log of x, which implies that e to the negative r equals x. Taking the derivative, we get negative e to the negative r dr equals dx. And so our new integral, because we get the infinite series from n is 0 of a to the n factorial. Our new limits become the natural log, by limit definitions, the natural log of 0 is infinity, the natural log of 1 is 0. But we'll just take this negative and use that to flip the limits of integration around. So we'll come up with this, and we'll come up with x is equal to e to the negative r, so we'll have e to the power of negative r and b. We'll have another negative e to the r for the differential. So this will be another minus r. And then the natural log of x is equal to nothing but negative r. So we get negative r to the power of n dr. Here we can pull the negative 1 out from the r term, equals 0. And here I'll also factor the r out of this expression here to get negative r times bn plus 1 and rn dr. We're trying to turn this into the case of basically e to the negative t times t to the n. To do that, we'll do another substitution where we'll let t equal r times bn plus 1, implying that t over bn plus 1 equals r. And the derivative here is just going to be dt by bn plus 1 equals dr. Now notice that this is also just a constant in the t world, so we'll pull this out of the integral. And we will have negative 1 to the n, a to the n, and factorial times bn plus 1. Then we get the integral from 0 to infinity of, so e to the negative r, bn plus 1 will just become e to the negative t, and r to the n will become t by bn plus 1 to the n. So t by bn plus 1 all to the nth power dt. Now this bn here is also a constant to the power of n, so we'll pull this out as well, and that will give us equals 0, negative 1 to the n, a to the n, n factorial times bn to the plus 1 to the power of n plus 1. And we'll be left with the integral, that should be an infinity, e to the negative t times t to the n dt. Now, to note that this integral here is just equal to n factorial. Given that, we can simplify the entire expression down into the infinite series or sum of negative 1 to the n, a to the n, get rid of the n factorial, bn plus 1, parentheses, n plus 1, and that is our final answer. That is equal to the integral of x to the ax to the b with respect to x for all a and b greater than or equal to 0. I hope this was at least a slightly entertaining video. If I made any mistakes, please be sure to correct me. But otherwise, I hope you enjoyed, and I hope to see you in the next one.